Buenos días. Good morning, everyone, and thank you for attending this IMB-CNM Talk session. I'm Carlos Domínguez. I am head of the Photonics platform that is running in the clean room of our institute. And to mark the International Day of Light, that was held last Friday, the integrated photonics team of the CNM would like to present two initiatives approved by the European Chips Joint Undertaking and the Spanish government, both with and both is involved our institute, and both initiatives are dealing with the development of photonic integrated circuits. The first presentation given by Joaquín Faneca, here next to me, concerns PIXEurope. PIXEurope is the European pilot line for the integration of advanced photonic circuits. This pilot line aims to stabilize the different technologies that will need to cover the whole value chain from fabrication up to assembling and validation of photonic integrated circuit, and with the hope that this contribution will help the European industry and academic institutions to use this kind of circuits. Next, Sabek, also next by me, will continue with another initiative, is PIXSpain. PIXSpain is the only one competence center in Europe focused on photonics integrated technologies. So the mission of the competence center is to disseminate all the technologies that we are developing and put it available also for the end users at the European level in order that we can exploit the results of the pilot line. So I will give you the word to Joaquín Faneca that will start with PIXEurope.
Thank you, Carlos. Really nice introduction. Okay, so first of all, we're going to talk about two different things today. We're going to talk about the pilot line and then the competence center. So first of all, I would like to acknowledge all the initiatives that the European Chips Act is carrying on. Like it's trying to push like different initiatives in the terms of chips to earn the European sovereignty in technology. And it has been divided in different things like design platforms, competence centers, and also pilot lines. I want just to outline here that IMB-CNM has been like working hard on these initiatives, and we have been involved in several of them. In the part of the competence center, we are part of two of them, Microelectronics Spain, which is related with electronics, and the PIXSpain, as Carlos was mentioning, is the only one that is photonics competence center in all Europe. Then we are part also of the design platform. And then in the pilot lines, we are also part of two of them, in APEX, which is heterogeneous integration. And we have a really strong role, and it's the one we're going to talk today in PIXEurope. Now they are launching another ones in quantum, but we will see how this is going. So this talk it's meant to be like, because it was the International Day of Light, the 16th of May. Unfortunately, we were in Brussels last week and we were not able to make it that day. So that's why we are pushing it to this week. And why was the May 16th the Day of Light? It was because this guy here, Theodore Maiman, was making like the first successful operational laser in 1960s. That's what that day it was 16th of May, and that's why later we have unified with UNESCO this day as the International Day of Light. This is going on since 2018. So UNESCO was like determining this day official since 2018. And here you can see like the first laser that this guy, the Theodore Maiman, was making. You can see that is exposed in Malibu, California. It's a nice place to live there, beaches and a lot of places to visit. And it's there in a museum. So I would like to introduce you to silicon photonics because mainly the majority of you maybe don't know about this topic. And silicon photonics is mainly the optical analog of the silicon microelectronics. The electronics, it was limiting in data transfer the speed and the bandwidth of the data. and silicon photonics has emerged as one of the technologies to try to overcome these drawbacks. The advantage is because if you're using silicon as well, it has low cost, and you can use compatible processes that you're using in microelectronics. Here, I just put you some cuts of the recent companies that have been working already in silicon photonics. I mean, NVIDIA was launching like 2 months ago the first processor made of silicon photonics, which was a big step for the community of photonic integrated circuits. Intel was working in silicon a long time ago, like 10 years ago. They were doing already try to do transceivers. So they always talk about moving data using light, and IBM is also talking always about silicon photonics as the future of high-speed data. So these are companies that have been working in silicon photonics for a while now, and NVIDIA has launched like a big processor like 2 months ago. So to sum up, mainly, the good thing about silicon photonics is that you can integrate optical and electronic components in silicon-based platforms that can support high bandwidth and low latencies, and you can have low power consumption because you don't have heat dissipation because of the Joule effect. You can do compact designs, and you can scale up. So that's important as well. So for you to understand the silicon photonics roadmap, everything started with different materials. People were doing photonic integrated circuits with gallium arsenide, indium phosphide, silica, lithium carbide. And the thing was that the silicon photonics was emerging more than the rest of materials because it was cheaper, but also because it was compatible with the processes and the equipment that were optimized already in microelectronics. So that was the main reason, because clean rooms were already optimized with processes and equipment for the silicon microelectronics. So they wanted to exploit these processes for trying to do photonics. Once they were achieving like lighting going through the chip in a passive way, the next step was trying to make tunable devices, trying to make active components. And that thing was coming with implantations like PN modulators or different materials that are called liquid crystals or phase change materials in order to make them tunable. So when you have tunability in top of the passive devices, what you can do is like the next step, which is programmable silicon photonics, which is called like reconfigurable circuits. So this is where we are at the moment, and what we are trying to make here is just to control from a software what is going on in the chip. So with path is selecting the light inside the chip. This one of the biggest companies in the world and the first one in doing a photonic configurable processor is in Valencia. It's called Ipronics. They have received a lot of investment, more than 10 million, and it's one of the pioneers on this case. We made them the first prototype here, and they are now developing like more like scaling these technologies. So for the guys that are like, and the girls as well, like that interested in the chip costs, it's important when we are talking about the scaling up, because all the time here in electronics we are doing like wafer size is important, but in photonics we need to know when it's worth it to scale up or not, because at the moment it depends on the production that you have, the demand of chips that you have per year. So you can see here the chip cost, and here is the PICs that you produce per year. Here you can see the wafer size. So 3 inches, 4, 6, and 8 inches. So you can see that for the 4 inches wafers, that is this black line here, only becomes cheaper if you produce around 15 million units per year. So that's when it becomes worth it to scale up. That's important to take into account, because everyone talks about the scaling, but it's not the same in electronics and in photonics. So if you want to scale up and you want to have the chip cost optimized, you need to take this into account. So the silicon-based photonics technologies that we are having at the moment, we have silica, which is the silicon oxide, but this one is not important at the moment in photonic integrated circuits because the dimensions that you need to produce a photonic integrated circuits are similar to the optic fiber. So in these cases, normally people go for optic fibers. So the main technologies that are going on now in photonic integrated circuits based on silicon components are the SOI, or silicon insulator, and the silicon nitride. Each of them has its advantages and disadvantages. Silicon has a higher index contrast, optical index contrast, than silicon nitride. So that means that you can reduce the footprint of the devices. You can put more components in smaller areas. You can optimize nonlinear effects. And the grating coupler, so the coupling between the optic fiber and the chip, is better in silicon than silicon nitride. Transparency is limited because silicon is transparent in the infrared, but not in the visible and in the mid-infrared. So the window of transparency is limited. You have 2 photon absorption in the silicon, and making multi-layer stacking or 3D integration is more difficult. It's more sensitive. That means that a simple error in the pattern of the lithography in silicon, it reflects or affects more to the response of your photonic integrated circuit than in silicon nitride. And the losses are higher than in the nitride. So normally we are talking about 1-2 dB per centimeter in silicon. And in nitride, we have it has been achieved 0.01 dB per meter in some cases of technologies that are on Europe. The good thing about nitride is transparent from the visible to the mid-infrared, so you have like a larger window to work on. You don't have to photon absorption in the infrared range, so for high-power devices, it's really important to use nitride. The refractive index can be tuned. You can, during the deposition process, you can play with the gases ratio and change the optical properties of the silicon nitride. And for nonlinear effects, so Kerr frequency comps and all these kind of applications, silicon nitride is the best choice in integrated circuits. The index contrast is smaller than the silicon, which that means that the footprint is higher. So that means I can put less components than in silicon, even though the footprint is quite small. And the grating couplers are less efficient than in the silicon platform. So just to sum up, like here are some of the characteristics. Also, one important is the birefringence, because SOI or silicon insulator is a crystal of silicon. You have like the birefringence effect, which you don't have it in the silicon nitride. Both are CMOS compatible, and here is an important task as well, which is the wavelength range, as I was mentioning. This is a study of the global roadmap around the world about photonic integrated circuits based on silicon nitride, which is a technology we developed at CNM IMB. And here, it's important to let you know that even though it's really small, because I want to show you everything, 70% of the market is in Europe about silicon nitride photonic integrated circuits. That's what Europe is trying to maintain. Also, in this part, we are appearing in the foundry and in the manufacturing technology. So IMB-CNM, we are always in foundries and manufacturing technology in terms of silicon nitride global map. In the PDK, even though we are not there directly, we have here VLC Photonics, which is acquired by Hitachi. And this company is owning a PDK that has developed together with us. So indirectly, we are also part of this PDK stuff. And all this community, not only about silicon nitride, but all about the photonic integrated circuits around Europe, was coming together in order to try to push a pilot line about fabricating photonic integrated circuits of different technologies. And that's how PIXEurope emerged, which is the pilot line number 5 of the European Union. So PIXEurope, as Global Photonics was saying, it was a problem. In the market, it was like approximately 8% of the companies or SMEs or startups that are approaching to us, they are in too early stage for us to do volume manufacturing. Okay, so we have a gap. We cannot do volume manufacturing because they are not in a stage to produce volume manufacturing. So PIXEurope is trying to cover design, fabrication, packaging, test, and reliability of photonic integrated circuits and try to cover this manufacturing gap that it was appearing. So what are we doing is lab to fab gap. We are trying to cover the TRLs and MRLs from 3 to 6. So that's done by all RTOs, the research centers. Here we have manufacturers. Here we have the SMEs, startups, and spin-offs. So how does this work is mainly you have an SME startup or a spin-off, and you make a prototype that all the RTOs or the pilot line is going to fabricate. And when you have proved and demonstrate this prototype, if these companies are ready to go to production, they will go to the manufacturers. The manufacturers, they will need the equipment and the process that we have optimized for these prototypes. So what we will do as RTOs is to transfer this technology to the manufacturers, and the manufacturers are the ones who are going to do the large volume. So that means we are not making any competitive thing against the manufacturers. What we do is we transfer the technology in order for the SMEs produce in large volume if they require. So this is like the first world pilot line that is going to cover this gap from TRL2 to TRL6 to make like a PICs production. This is the consortium of the pilot line. So we have like 11 different countries, and we have 20 entities in which Spain is leading. So ICFO is the coordinator of the PIXEurope proposal. and Spain is getting around 135 million of the 400 million total budget. And it's important to notice that 30 million of these 400 is coming to our center. And it's also important to notice that from these 400 million euros, around half of it is going to go for equipment. So it's going to go for like different lithographies and technologies developing for the photonic integrated circuits in different parts of Europe. This is the distribution of the pilot line. We have different parts in which these are called the monolithic PIC platforms, which are the different materials that are used for producing photonic integrated circuits. We have silicon carbide, silicon nitride, indium phosphide, germanium and silicon. We will explain later why we need these different materials. And this is going to do the PICs platforms. Then we do hybrid integration because we need to combine these PIC circuits with different technologies in order to produce lasers, for example, or photodetectors. Then we have also integration with electronics, packaging, test and reliability, and the demonstrators. We are leading the silicon nitride part, but also we are in charge of all this work package about the different technologies of the PIXEurope. So we will be also in charge of checking that all the photonic integrated circuits around the different technologies are evolving properly. So PIXEurope has horizontals and verticals. So in one way, we have technology and innovation in which we can do like application-specific or programmable devices. We can have also optoelectronic interconnections or design and fabrication of the different materials. And then applications which are going from the typical telecommunications in optic fibers or data centers to neuromorphic computing, artificial intelligence, sensing, LiDARs, which is automotive, consumer electronics, health, in which we are doing photonic biosensors, or security and defense, which can be like cryptography, information, all the stuff. But apart from that, what we need to do also is to do education in this pilot line, transfer technology to different entities, internationalization, because we need to encourage to everyone in Europe to push this this proposal, and the engagement of the companies and the end users. So this is coming with governance and the ecosystem, okay? So for you to understand the PIXEurope phases, there are like 3 big phases for us. One is the grant period, so it's starting like probably at the beginning of June, we're going to have the kickoff, but August, September is going to start the pilot line. From 2025 up to 2030, we're going to have the grant period. So it's where we are funded, okay? We are already starting, but we need to have like an industry engagement phase because we need to engage the industry in order to use the technology that we are developing. And at the end of 2030, we need to have the pilot line operative. So it needs to be operating. It needs to be able to produce the chips in the different technologies that we have developed during the process. What happened when these 5 years has ended? So when these 5 years has ended, we have another 5 years, which is called the sustainability period, in which we need to have self-finance and be able to be self-financed by our own. So that means that we need to sustain the pilot line with our own resources. And this is going to be a period of another 5 years. So for you to understand the PIXEurope operations, we have a centralized gateway, which is this one. And we have like inside PIXEurope, as I was telling you, like design, chips, fabrication, hybrid integration, packaging, and test and reliability. All this is what gives you like what is called process design kit, assembly design kit, and test design kits. So when you have all this fabricated, you need to do like a demonstrator. Why we do demonstrators with all the technology that we have developed in PIXEurope? Because we need to demonstrate and validate the technology and the processes. So with a demonstrator, we are able to demonstrate that all these processes are compatible with the different centers, and we will also demonstrate the operation of the pilot line. So that will go through a gateway, which PICs end users, PIXEurope end users will go here to make prototypes or develop like the multi-project wafer or develop any design that they want to do. Once they have done this, you can go to manufacturers in order to transfer the technology and scale the value of manufacturing. So this is the way of operating of the pilot. But as I was mentioning, we have also an important role in training, and we have like hands-on and online training in design, fabrication, packaging, and test. But at the same time, also, we can do it's mandatory to make like internal training, but also external training. So that means for people that are inside the pilot line and for people that are outside the pilot line. So we can do courses outside and inside. And now we are going to focus more in the platform that we are developing here at IMB-CNM and what are the challenges in PIXEurope in this technology, okay? So in silicon nitride photonic integrated circuits, we have challenges in terms of like light generation because it's not a material that can emit. So here during PIXEurope is going to be still poor. But in the other functionalities like modulation, detection, nonlinear, and low loss, and the integration with electronics, we are going to go one step further along the project of PIXEurope. So that means we're going to scale in the functionalities. Also, we are going to scale and do better manufacturability in terms of technology and commercial manufacturability. We are going to improve also the wafer size, and we are going to improve also the foundry capacity because we're going to have all the people in photonic integrated circuits involved in this project. The integration density is going to be improved because we are going to buy in a lot of places also better tools of lithography. So I put here you an example, but this is going to be done for all the photonic integrated circuits technologies, so silicon germanium, indium phosphide, but I put you the one in nitride. So here at CNM, we will work at 150 millimeters, but then 20 and Leti, we're going to scale up this technology. So you don't need to think about this with like different entities itself because all this is done in the pilot line. So at the end of the day, we will transfer to each other technologies because we are in the pilot line. So even though we are different centers, we need to think of this about is one. So the thing is, Theality has the capacity to scale up to 300 millimeters, and that's why they are making this scaling. And before making the scale up to 300, we need to go to 200 because of the stress of the wafers with nitride. So we need to go step by step. So we have silicon nitride in the near infrared, which is the technology that has been most developed in the near infrared range. And here we need to make an improvement during the PIXEurope in functionality and integration. And how we can make this? We can make this in different ways. It can be based on the material, in the components, or in the technology itself. So what about regarding the material? So if I want to improve the functionality of the integration of the material, what I can do is refining the silicon nitride stoichiometry. So I will tell you later about this, but we can refine the silicon nitride stoichiometry and we can do thick, thin, or ultra-thin silicon nitride. This also depends on the stress on the wafer. Components, we're going to do edge couplers that are like being less than 1 dB. Modulators, they're going to be improved. We're going to do frequency comms and multi-level components. That means we're going to combine silicon and silicon nitride technologies. And in the technology itself, we're going to reduce the losses. We are going to improve the confinement of the waveguides inside the photonic integrated circuits. We're going to improve the integration density, which means more components in the same area. And we're going to scale up as well all the processes. So one way of tuning the optical properties of the silicon nitride is with laser trimming. So that means we have our silicon nitride waveguide, and then we do like the photoresist, the lithography. And then with a femtosecond laser or with a pulse laser or with implantation, we can tune the optical properties in the region that we're interested in. That means it's a post-fabrication tuning. So we are able to change the optical properties, the refractive index, imaginary and real part, after the fabrication. So this is easy alignment, and you can correct things after the fabrication. Another way is changing during the deposition. So that means during the fabrication process. So you have your silicon nitride stoichiometric, for example, and then you do your waveguide pattern. And after that, you do another silicon nitride with other properties. So that means that you are going to change the ratio of the gases of the deposition. In this case, for example, ammonia and sealant. And then you deposit, you also create your waveguide. So you are doing, in this case, 3D stacking, but this process can only be tuned the optical properties during the deposition. When it's deposited, the optical properties has been fixed. So one important part is the silicon nitride modulators in the near infrared. At the moment, in the technologies that are offered in Europe or is using thermal tuners, why is that? Is because it has a high yield and is CMOS compatible. And that's the main reason. But it has problems. Which problems? It consumes a lot of power, has high footprint, and they are slow in the switching. So different materials are emerging in order to overcome these drawbacks, like graphene, stress, phase change. But Mainly, not all of them are CMOS compatible, and not all of them has a high yield, even though they have good characteristics. So one of the solutions is using silicon to make the modulation in the near infrared. Why? Because it has a high yield, it's CMOS compatible, and you reduce the power consumption compared to the thermal tuner, and also you improve the speed. So this is something we have been already developing here at IMB-CNM. We have been working in silicon nitride waveguides with PN junctions on top and underneath. On top with amorphous silicon, because you deposit the silicon itself, and underneath if you use an SOI wafer with crystalline silicon. You have like lateral and vertical PN junctions. The verticals are not working really well, or they will not perform really well, but the lateral ones are promising. So that's the approach we are taking at the moment. And all the things I was talking, it was in the near infrared. But now one of the targets of PIXEurope is also to expand the wavelength of the photonic integrated circuits, not only for the near infrared, but also from the visible to the mid infrared. In the visible, one of the targets is to create a universal waveguide extractor to have high confinement and create a component library, so a PDK. And in the mid infrared, we're going to integrate 2D materials with the silicon nitride, and we will develop also a component library. So for you to understand now why we're using different materials is because normally in electronics you have silicon, and with silicon you can play with everything. But in photonics, the problem is the transparency of the material. In our case, for example, if you want to use SOI or silicon itself, it's not transparent under 1.1 microns. So if I want to work in the visible for photonic integrated circuits, I'm not able to make it because it's absorbing. So it's taking all the light with it. So that's why we need, for example, if you want to go up to 6 or 9 microns, what is used is silicon germanium. When you want to go to ultraviolet, you need to use alumina. When you want to go to visible, people are using silicon nitride. And for example, in infrared, the most used ones are SOI, silicon nitride, or indium phosphide. Indium phosphide is more expensive, but it's an active material. So it has the advantages that it can have lasers integrated already in the platform, which the other ones cannot. So that's why PIXEurope has different materials for photonic integrated circuits in order to cover all the spectrum. Here is something we have been doing also here at IMB-CNM. I wanted just to show you a bit of not everything we are doing, but the advances that we have been doing during these years in the fields that are related with PIXEurope. So these are some of the structures we have been fabricating, and these are some of the measurements that the photonic platform have been doing. So this is in the red and in the green. Now we are also targeting the blue. We are going to order the laser soon and try to characterize the blue one as well. So PIXEurope methodology. Now that you understand that there are different materials in photonic integrated circuits, so that's the way you depart. You select the material that you want to work in, and then you decide like, okay, with this material, I can work in the visible, the infrared, or the mid-infrared. So with this, you do your designs and simulations of your structures, and you then fabricate it. So you have a process development, and you need to do a parametric test and validation of the technology. This is only of the technology. When you have this done, and then you integrate this passive circuit with another photonic integrated circuit, for example, or you want to integrate this photonic integrated circuit with an electronic circuit, you can do this with hybrid technology. So it can be PIC-to-PIC or PIC-to electronic integrated circuit. All this, when has been optimized, you do what is called PDK, a process design kit, okay, in which you have optimized all these building blocks. Once it has been fabricated, you do the back end of the line processes, which is basically the cutting or dicing. You can also do bonding. And then you do the testing, now optical testing. So that means you are testing your photonic integrated circuits in terms of losses and characteristics of the structures that you have patterned. And with this, you do what is called test design kit. When it has been tested and is working properly or according with your targets, you do the assembling, which is basically the packaging. So you can do interposers or chiplets, which is basically the chiplet is to have different modules in the chip. And with that, you create the assembling design kit. So this is crucial in order to go back to the simulation. So what you provide to the end users are PDKs, TDKs, and ADKs for their design. When they have this, they can create their PIC system, check the reliability, and create their demonstrator. So that's why what you give to the end users are ADKs, PDKs, and TDKs. Also, it's important to know or to understand that when you have a lot of PDKs with different materials, you need to make them compatible. And this is not going to be an easy task. That means that, for example, if I'm creating a PDK in the visible range with the corresponding structures, and I want to have also then combine this with another PIC, or I want to combine this with an electronic integrated circuit, I need to have compatibility between the PDK of the photonic circuit and the PDK of the hybrid circuit that I'm creating. So that needs to be like a hard work in this pilot line in order to check that all these PDKs are compatible. And all this will be available through the Chips JU Design Platform Hub, which is what we were talking at the beginning, one of the targets of Europe as well, to have everything, not only photonics, but all the pilot lines in the Design Platform Hub. So for you to understand the PIXEurope end user, so we have designers, of course, people who want to design and then we want to fabricate with us. Then we have manufacturers, because we will transfer technology to them. We have vertical integrators in terms of demonstrators, and then the suppliers. We need to supply with like the wafers, the materials, etc. So just for let you know, like a number more or less, like we have like identified more than 150 end users of the pilot, and we have received like for the pilot line more than 60 letters of support from companies as well. So the specific objectives of PIXEurope, for you to understand, is to, I think Carlos was mentioning at the beginning a bit of that, but it was developing mature and standardized breakthrough PIC processes. We need to offer advanced services, so multi-project wafers to people, and advanced packaging and testing. We need to unify Europe's top research organizations, because at the moment we have really good, and the market of photonic integrated circuits is in Europe, but we have it in different organizations. With this PIXEurope, we're going to unify all the organizations to establish the first world's PIC open access pilot line. We need to foster also the PIC industry in Europe, establish high and visible coordinated training for students. This is a problem we are currently having. It's not a lot of masters. Now there is more, but I'm emerging in the recent years, masters of photonic integrated circuits and people that understand how a photonic integrated circuit works. And also an important part is the collaboration that we will have with the other pilot lines as well. So for you to understand, like these are the other three pilot lines, and these are Apex, which is the one we are going to be working close with, because they are doing heterogeneous integration with electronics and photonics. And PIXEurope is going to be coordinated with all these platform pilot lines, and also with projects that were not as big as the PIXEurope, but were big enough, like 7 million budget in Europe, with this PIX for Life, for example, or PIXHub or JPIX, which are the first kind of projects, big projects that in Europe were carrying on. Now they are going to emerge the quantum pilot lines as well, and PIXEurope will have a big role there as well, because one of the lines of quantum is the quantum photonic integrated circuit. So we will need to give support on this pilot line. Just to conclude, I think it's important to acknowledge people that have been helping us with all this, because it's a big grant and a lot of work under this. The Silicon Photonics team, because it was like dedicating a lot of efforts for us to like allowing to write the proposal. Gonzalo Espino and Eva Alvarez that have been like working hours in the terms of negotiation of agreements with Europe and with all the supporting administration. The GTQ for providing the environment and freedom to develop the work that we have been doing. IMB-CNM, because they have continuously assist us and back us with all the process. And I think that one of the most important, even here at the last, is the clean room engineers and staff, because just to remember, this is a pilot line. And I think that without the excellence and dedication of the clean room staff, we will not be able to develop the technology that we are selling in the pilot line. So I think the technology here is crucial, and it was only be able to develop the technology because of the ICTS. So with that, I would like to conclude, and thanks for your attention.
Yeah. Questions will be given at the end.
Good morning, everyone. Thank you very much for being here today. Now I will be introducing you to the PIXSpain Competence Center, a crucial part of Spain's role in the growing of European photonics and the semiconductor ecosystem. We will explore what photonic integration is, why it matters, and how our center is helping shape the future of the innovation in Europe. So here we have the summary of the principal points we will talk about. So to begin, PIXSpain is a competence center coordinated by, among others, the IMB-CNM. As you know, we are deeply involved in photonics, a technology that uses light to transmit and process information, much like electronics uses electricity. Our platform specifically on focuses specifically on photonic integrated circuits, or PICs, which are miniature devices that integrate multiple optical components on a single chip, a game changer for sectors like communication, health, and quantum technologies. According to Yole Intelligence, which is a consulting firm specializing in the strategic analysis of markets, the supply chain, and technological development, this related to the semiconductor industry and adjacent industries, the evolution of integrated photonics die market from 2021 to 2027 is from $152 to $970 million general growth, being data center transceivers and consumer health who takes over the majority of the volume. Here, developing die PICs is no easy task. The circuits require materials with very specific optical properties, and at IMB-CNM, we use the silicon nitride, a material that allows for very low losses, low signal losses, and works across a wide range of wavelengths, from the visible to the mid-infrared light, as we have seen previously with Joaquín. So our photonic platform is designed for versatility, so we can fabricate different waveguide geometries and include features like thermo-optical tuners, selected areas opening for biosensing, and specialized couplers to connect the light signals efficiently. This flexibility supports a wide range of use cases, from telecommunications to biomedical diagnosis. To make this technology more accessible, we use a model called the multi-project wafer, or MPW, instead of manufacturing one design per wafer. MPWs allow many users to share a single wafer, drastically reducing the cost and time required. We collaborate with design houses and foundries to offer this service in streaming and cost-effective way. In this case, we talk about VLC Photonics, with whom we have developed the PDK some years ago, and what we offer nowadays. So far, we have completed 7 MPWs run, and we are preparing now the 8th. We have worked with over 50 consumers, delivered more than 600 wafers, and collaborated with international organizations like Nokia and the University of Bristol, among others. Our work has led to over 60 published scientific articles and numerous conference presentations. So the next approach is the due for specific needs, which is the customized approach. So this requires longer development time and higher investment. It allows full control over materials and process, which is ideal for small product series or cutting-edge research. Furthermore, we are also pushing the boundaries by developing a design kit that you can see the first experiments we did. And this is for PICs in the visible light range, opening new possibilities in sensing, imaging, and quantum applications. So the next point is the photonic initiatives the IMB-CNM is involved. PIXSpain is deeply integrated into the broader European photonic community. So we collaborate with major organizations like SECFO, EPIC, and EPIXFab, forming part of a dynamic network that spans academia, startups, and industry leaders. These alliances are essential to collaborate and accelerate innovation and lower the boundaries to photonic adoption. The first example is of the Spanish foundries ecosystem for PICs, which is formed by 4 institutions. 4 of them are foundries. The IMB-CNM is for the development of the photonic integrated circuits in the silicon nitride, which are the passives. Graphenea will deposit the graphene modulators. Spark is to deliver the active components, such as the lasers and photodetectors. And finally, the UPV fab will be charged to integrate all of them in a single chip, which is the functional one. Also, we are a highly active member at the Southern European cluster in photonics and optics, side by side with more than 164 industries and academic groups. The European Photonic Industry Consortium, EPIC, is a non-profit association headquartered in Paris, and it supports the photonic community by organizing regular workshops, conducting market research, and fostering strategic partnerships with over 800 members across 35 countries. EPIC promotes the growth of the photonic sectors and enhances the global competitiveness of the European photonics industry. PIXFab is more focused on academic, with over 50 academic and industrial organizations, and also promoting silicon photonics in Europe and globally, because also there are collaboration with Asian and American institutions. So here we will talk about the main core subject of this presentation, which is PIXSpain Competence Center. So in this diagram, we see the outline and the governance structure and the 3 main pillars of the European Chip Act, overseen by the European Semiconductor Board. The first one, this pillar 1, the Chips for Europe initiative focuses on infrastructure development aligned with European Union research programs and supports startups and SMEs. Pillar 2 addresses the security of supply by promoting the establishment of first-of-a-kind semiconductor production facilities, whereas the pillar 3 focuses on monitoring and crisis response. Chips GU plays a key role in implementing Pillar 1. The next is to focus a bit more about the Competence Center, which are a core part of the Chips for Europe initiative. PIXEurope aims to support SMEs, startups, and the research in semiconductor development and researchers in semiconductor development. The services include training, R&D access, design platform, and pilot lines. The next image illustrates the ecosystem and integration model of the PIXSpain Competence Center within the Chips for Europe initiative. Here is a concise summary, as we have seen before with Joaquín. We have the PL1 to PL4, and here the CPL5, which is the PIXEurope. And we are involved into the PL3, the PIXEurope, and now we're in the PIXSpain Competence Center with the Microelectronics Competence Center, which is more focused in semiconductor performance. So, also is part of the European Commission's Chip for the Europe initiative, which aims to strengthen Europe's autonomy in semiconductor technologies. The initiative is structured around 3 pillars: building infrastructure, securing supply chains, and enabling crisis response. It supports and connects universities and the research organizations, industry looking to adopt photonic technologies, students and future talents, capital investors and funding bodies, pilot lines and design platforms. In summary, PIXSpain Competence Center is a strategic gateway facilitating the development of advanced semiconductor and photonic technologies by integrating key infrastructure such as pilot lines, design tools with diverse stakeholders like academia, industry, and funding agencies. As a Spain's Competence Center, PIXSpain is tasked with reinforcing European scientific excellence and helping technologies address social and environmental challenges. We provide services such as design support, pilot line access, and R&D advisory, all aimed at empowering startups, SMEs, and the researchers. This initiative is co-funded by the European Union, providing up to $1 million per year and country with free or reduced cost services for small enterprises and public institutions, ensuring equitable access to advanced technology. Finally, we will talk about the more specific role of the IMB-CNM in this PIXSpain, which is tech support and R&D advisory. So the CNM role in this PIXSpain, as we have said, is tech support and R&D advisory, which is to provide the technological and the research guidance to SMEs and startups, acting as a bridge between European Union level research and local semiconductor ecosystems. Its activities include coaching and R&D and infrastructure, facilitating access to design platform and pilot lines, offering legal and business support, and organizing joint training with other competence centers. The goal is to enable technology transfer, connect companies to experts, and integrate local actors into European R&D initiatives. This support empowers smaller companies to innovate without in-house research capabilities and strengthen their position within the European semiconductor landscape. Well, we have laid out an ambitious roadmap from establishing tech transfer protocols and joining European Union network to launching advisory programs and enabling cross-border projects. Our long-term vision is to expand services across Europe and explore emerging areas such as quantum photonics. And before I close, here are some of our key contacts in Spain and Europe. Soon we will provide the person contact of the other institutions that we are here to collaborate with. So whether you are from academia, startup, or part of a larger company, we welcome you to be part of this journey. And as we have seen, the PIXSpain Competence Center is more than a facility. It's a gateway to the future of photonics in Europe. And I would like to mention something that I think very important also, which is the high importance of our clean room personnel, since the clean room is the heart of our institution as far as I believe. So just to render thanks to them, send a big hug to our colleagues Carlos and Elena, and wish them a prompt recovery. And encourage all to keep pushing the boundaries of what's possible together. And this is all from my part. Thank you very much. And if you have any questions, please, you can ask.
Well, time for questions. We have 5 minutes.
Yes, yes.
5 minutes for question.
Also from the Zoom, if you want to move the microphone, we can hear you.
So are you planning also in this pilot line to integrate in the silicon nitride the emitters and the detectors in the same chips, or it's just more the passive component and the modulator?
At the moment, mainly it's modulators and reducing the footprint of the devices with the new lithography that we will have. But also it's considered, photodetectors, for example, are considered, and also lasers as well, with hybrid integration. So this is something is going to be as UPV in Valencia is in charge of the hybrid package. So maybe they will try to develop the lasers. That's what we was calling about the peak-to-peak. So maybe they will probably develop the laser itself with the PDK of the laser, and then we will develop the PDK with the silicon nitride, and then we'll need to place the laser on top of the nitride and couple the line there. So everything is considered. I mean, and it's one of the goals of the objectives of the pilot is to put lasers on top of the nitride. Even though we have been working on this already with them.
We have an ecosystem with SPAC, which is in Vigo, and Graphenea to accomplish all these components into a single functional chip with active components such as laser and the photodetector as well.
Hello, this is Miguel Zavala. Can you hear me?
Yes.
Yes.
Yeah. Thank you for the talk. I want to ask especially Joaquín, because you have shown in an early slide about the advantages and disadvantages of the silicon nitride or the SOI, and we are focusing mostly in the silicon nitride. I have seen that especially the disadvantages of silicon nitride are covered by the silicon of the SOI. So I wonder if we are trying to combine both technologies because they are compatible. So I don't know.
Yeah, that's an excellent question, Miguel. And that's something we have been actually talking recently about this, and we would like to combine both technologies. So the ideal thing, that's why we have like a multi-level component system I was talking about, is trying to combine. For us, it will be interesting to have an SOI underneath, and then having silicon nitride on top. So that will mean that we will exploit both advantages of both technologies. So we will have kind of two layers, one SOI layer underneath that we can play with the silicon, and then on top of that, the silicon nitride. That's something we are trying to push, and probably soon Cleanroom will hear about this because we will try to develop that.
What Joaquín means soon, for me means
Yes.
that we will need a CMP equipment that,
Exactly.
because in order to integrate the silicon nitride on top of the silicon over insulator, we will need very smooth surfaces in order to reduce the losses of the upper layers.
Planarized.
Yes.
The problem we have right now is the parameterization. That's why we didn't start sooner, is because we need the parameterization in order to combine both technologies.
We have started some assays to planarize, especially with Javier Sanchez using spin on glass. But the spin on glass serves for things we are pushing a lot with the spin on glass, so the performance we are obtaining by now are not enough. That's why the CMP, I think, is the key equipment to push ahead with this performance.
But I think the answer is yes, Miguel. We want to combine both, and that's something we will try to push.
Okay, yeah, thanks.
There was a question. Well, my question is more organizative, because I see that you have the PICs, the pilot line, okay, in Europe, and the platform. I suppose that both are working together, no? And then my question is, are you planning to have more personnel? Because you with the fees, all this, I think it's impossible.
More personal? Where?
No, in the clean room, I suppose that
Yes.
you will have more.
No,
suppose.
in fact,
But for the organization of all that,
Yes.
I think
in fact, there will be a very increase in people for that, for the pilot line, but most devoted to their people, not as we normally contract. That means that people would be devoted to research and development of research projects, something like this. In that case, would be technical people, more technical and more devoted to process development or for PDK development or simulation and so on, not with the scope to have a scientific career after that, more technological career if possible.
And there is also a question by
Sí,
Miguel.
Miguel?
Hi, can you hear me well?
Yes.
Okay, so yeah, following up on the last two questions, you mentioned the CMP and also the incoming personnel and so forth. I wanted to know, of course, what is the timescale for that equipment, and also if there are plans to buy any other additional equipment.
The plan for equipment procurement will be 3 years. That means so far the project start, we have a compromise with a Chips JU that in 3 years we will have all the equipment running and operated on the different foundries or hosting sites for the different partners. That means that we will have all the equipment running and operative 3 years. From that point out, we have to develop the new processes or to stabilize the processes and to start the interoperability between the different hosting sites. So, but 3 years is the top. That means that not means that all the equipment will be buy at the first year, but some of them, in fact, the more difficult to start up. That means CMP, for instance, or Deep UV, in our case, would be the first.
Okay, but then you mentioned the CMP and the DBUV. Are there any other plans for additional equipment?
Reactive ion etching, scanning electron microscope, a track system, but possible connected directly to the DBUV, and other equipment.
Okay, very good. Thank you.
Please.
Yeah, I think like 2/3 of the budget that we have. So from the 30 millions, around 20 millions are going for equipment. So
Exactly.
that means that 2/3 of the budget that is incoming for the center, it's for equipment.
Thank you.
Welcome.
Thank you for the talk. Talking about the equipment, I saw that one of the ways you wanted to improve or modify the waveguides was like to laser sort of annealing. So is this one of the equipment you want to acquire, or you're gonna do it outside?
No. Laser trimming will be not an equipment available here. We are in contact with different groups here in Spain that offer the services to do that, and they are very interested also to search for new applications of their equipment, so we can work together in development this kind of processes. For instance, one of the processes that we are also requiring for the photonic integrated circuit chips is the cutting with laser. That is a very cutting dice with a wafer dicing, but with a laser, so that we have smooth sidewalls and it's more easier to do the back coupling between the optical fiber and the photonic circuit. That is a service that is not available right now in Spain, but there are some groups in El País Vasco, in Basque country, that they're very interested to develop this kind of processes.
It's really expensive right now to kind of do laser cutting.
In fact, now the dicing we are performing here in the IMB-CNM is with deep reactive ion etching that we developed with Brussels. And by now it's okay. But I think to develop the dicing with the femtosecond laser will be like the perfect condition.
So we'll have close collaboration with them.
Yeah, but this is not actually in PIXEurope. The one that I was putting in laser trimming is an example of things that we have been doing also to change the optical properties of the nitride. But for the laser trimming, it's with the lasers, it's not the main goal of the PIXEurope. It's something also we're doing
In the group.
Yeah.
Yes.
Yeah, research.
Yeah, we'll be more in the PIXEurope. We'll be more changing the properties with the position ratio of the gas. So we have the position 2 with the LPCVD, and then we just change the ammonia and silicon to the ratio in order to change it.
So thank you very much for coming, and up to the next section.
Thank you.